starting. All attendees are in listen-only mode.
Good afternoon and welcome to the 2018 New England Greenhouse webinars. My name is Jeffrey Joy from University of Massachusetts Extension. My co-host today is Rosa Rodales from University of Connecticut. The webinar series is a collaborative effort of UMass Extension, University of Connecticut Extension, and University of New Hampshire Extension, and is sponsored by Sungrow Horticulture and Blackmore Company. The theme for the webinar series is Growing Healthy Roots, and the title of the webinar today is Understanding the Components of Growing Media, and our speaker is Dr. James Outland, who is a research scientist with USDA Agriculture Research Service. If you have any question during the webinar, please type it on the question box, and at the end of the webinar, James will answer the questions. After the webinar, there will be a short survey. Please complete the survey before exiting the webinar. Now, before I pass the controls to James, I'd like to mention that the recordings of the webinars are posted on the UMass Extension Greenhouse and Floriculture Program website. And at this point, I'd like to pass the controls to James to continue with the webinar. Okay, James, it's all yours now.
Okay, well, thank you for inviting me. Is the proper screen showing now?
Not yet. You need to go to your... Okay.
Okay.
Yeah.
Well, thank you for inviting me. So it was quite a challenge to get all of this information down into 30 minutes, but today I want to talk about the properties of growing media. And one of the most respected scientists that study substrates is Dr. Bill Fontenot from NC State University. And he said, making media is similar to making soup, and you need to learn to shift your thinking from ingredients and components to properties and parameters. So we could go through a litany of different substrate components and their properties, but a lot of the information is available on the internet already. And what I want to talk to you instead is about what happens when you combine these components, because typically when we develop substrates, we are combining peat moss and perlite, or pine bark and sand, or pine bark and peat moss. So these are combinations of several different components, and the combination of those components is very unpredictable. And I'll give you an example. If you were to fill a container with sand, that container would hold very little water. Sand drains very freely, as does pine bark, but when you add sand to pine bark, it actually increases the water holding capacity. So logic may tell you that adding something like sand to pine bark will increase the drainage, but in fact the exact opposite happens. It tends to hold more water, and we'll discuss why that happens later, but it basically has to do with the way sand will nest in between the larger particles of pine bark. So what I want to talk about today are how these how we can measure and understand the properties and the parameters of substrates, and that will give us more information on making decisions in managing our container crops. Now, I want to start out with this because there are some differences between nursery and greenhouse crops. I work a lot more with nursery crops, but all the things that I'm going to discuss today can be applied to both nursery and greenhouse. Typically, nursery crops are grown outdoors in large containers, and pine bark, at least in the eastern United States, is the primary component in the potting mix. These are typically woody plants, although we can grow some herbaceous and ornamental grasses and those sorts of things in smaller containers. These typically have longer production cycles. Because these plants are larger, they tend to be more robust and less sensitive to changes in the substrates. We'll talk about that a little bit later. And typically, we're using coated or controlled release fertilizers on these crops. Now, in contrast, greenhouse crops are in some sort of protection under glass or in a hoop house. They're typically much smaller containers. They use sphagnum peat moss as the primary component. Typically, these are herbaceous crops. They have very short production cycles, and they are more sensitive to changes in the substrate. Now, this is just how I differentiate between nursery and greenhouse crops. And other people may have different ways of categorizing these things. So keep this in mind as we're talking about some of these properties, but understand that all the things that we're going to discuss can be applied to both types of production systems. So you may have seen this before. A good container media has basically 4 functions. First, to provide a reservoir for water. Second, to allow oxygen and gas exchange for roots. These 2 things, as we're going to see shortly, these 2 things are very linked, these first 2 properties. The third one is retain nutrients for plant uptake. This is basically what we consider the chemical properties of the media. And then the fourth one, which we will talk about in the context of substrate stability and shrinkage, is to provide anchorage for the plant. So, consider this crude drawing I have of a container, and it's filled with a substrate. This substrate could be bark or peat or whatever you want, but just consider that these are substrate particles. What surprises most people is that when you look at the volume of the pores within a container and a typical substrate, about 85% of the volume of the container is actually pore space. Very little of the container volume is filled with actual particles, only about 15 to 20%. But consider this container. One of the things that we could do, imagine if we somehow plugged the holes up on the bottom and we filled it up with water. This is in fact how a lot of scientists will measure the total porosity. If we can measure the volume of water that fills these pores, then we would know the total porosity. Now imagine we drained that container. And you'll notice that some of the larger pores empty out, and then these would of course be filled with air. There will be a film of water around all the bark or all the substrate particles, but some of the larger pores will empty out and be filled with air. Some of the smaller pores will still be filled with water, and this is especially true near the bottom of the container where we have this zone of saturation. But this is, when we talk about the airspace, it is the volume of this container that is filled with air after it's allowed to drain. And the water holding capacity, or what some people call the container capacity, is simply the volume of the container that is filled with, or that is comprised of water after the substrate is allowed to drain. And it should be clear, but the total porosity is really just a sum of the airspace and the water within a container after it's allowed to drain. So in fact, if you have your physical properties measured at a laboratory, there are not too many laboratories that will do this. NC State is one that will do this on a commercial basis, measure the physical properties of your media, but you will notice that the total porosity is in fact the sum of the airspace and the container capacity or the water holding capacity. Now, this just is a somewhat magnified view of that previous image we had, but notice that, again, all the particles will be surrounded by a film of water, and some of the smaller pores will be completely filled with water even after drainage. What happens sometimes is when we add another component to the media, especially if they have very fine particles, they can fill in some of these larger pores and thereby actually hold more water. And this is in fact what we talked about earlier in the presentation. When you add sand to a very coarse pine bark, you actually fill in, or it's not the right word, but in essence, you clog these larger pores and you create greater water holding capacity in that media. One of the very important things to consider when you're looking at changing your substrate or adding different or new components to your substrate is the relative particle size distribution of these different substrates. When you add a very fine textured material to a coarse textured material, you will tend to increase the water holding capacity and decrease the airspace in that media. Now, the ideal ranges for nursery or for container crops, for total porosity is 70 to 85%. Airspace would be 10 to 30%, and the water holding capacity or the container capacity should be somewhere between 55 and 65%. The container capacity and the airspace are very closely related. And consider this chart. This is some measurements that we took here in our lab. What we did was we took pine bark and we added 0, 10, 20, or 30% by volume peat moss. And when you add peat moss to pine bark, because peat moss typically has a finer texture, it tends to, well, first let me explain. In just 100% pine bark, what we have is 31% airspace. So that's a little high. Pine bark alone tends to be very freely draining, so it does typically have a high airspace. The water holding capacity is 54%. So when you add these two components together, we get the total porosity, which is 85%. And the solid component of 100% pine bark would be about 15% by volume. Now, as we add more peat moss, the airspace tends to go down as you begin to fill up some of these larger pores within the pine bark, but the water holding capacity increases. And what we often see is the total porosity stays fairly stable. As the airspace decreases, the container capacity will increase. So these two things offset each other, while the total porosity typically stays somewhere between 80 and 85%. And that's typical for most container substrates. And I threw this slide in here just to add some perspective to containers versus a typical field soil. Especially some nursery growers do still grow in soil. In a typical field soil, the total porosity is only about 50%, and that's about equal percent of airspace and water holding capacity. In container substrates, our total porosity is 85%, with 25% airspace and 60% water holding capacity. So our container substrates hold a much higher volume of water than a typical field soil. And this is, it's a good thing too, because our containers have a limited volume. Whereas plant roots can continue to explore the soil, find other sources of water. They can grow laterally and they can grow down into the soil profile. The limited volume on our containers, we need more water holding capacity so that those containers can, the plant can survive in that container without being irrigated constantly. So I want to talk about some of the chemical properties. And when we talk about the chemical properties of media, the things that we're most interested in are the pH, the electrical conductivity, which is really, pure water does not conduct electricity, but as you add salts and other materials to water, then electricity flows a little more freely. So by measuring the conductivity or the electrical conductivity of a water or solution, we know about how many salts are dissolved in that solution. So when we measure the electrical conductivity of a solution from our containers, what we're really getting is a gauge. It's a very loose gauge, but we're getting a gauge of how much fertilizer is dissolved into that solution. So the higher that EC value, the more fertilizer salts are in solution. Now the problem is we don't know which fertilizer salts. We assume that most of it is nitrogen and to some extent phosphorus, but we really don't know. So it's a good value to make decisions on, but it's not terribly informative. We just know that the solution has more salts, but we don't really know which ones. Now we can also determine which nutrients are in this solution. Typically that has to be done at a commercial laboratory. Most nursery and greenhouse operations don't have the equipment to measure the actual nutrient concentrations, but we can determine the pH and electrical conductivity. Now, here's a very important point. When we consider the chemical properties of the media, we are really concerned about the chemical properties of this solution that is in the media, what we call the substrate solution. The pH will drastically affect the solubility of nutrients in that solution, which will then affect plant uptake. Now, one thing is very important to point out, and I didn't write it on the slide, but this is a very important concept. Roots can only absorb nutrients that are in solution. They can't just pluck nutrients off the surface of these particles. That nutrient has to be in solution within this substrate solution in order to be taken up by the plant. One of the most important factors that affects nutrient solubility is pH, and that's why nursery growers and greenhouse growers are so concerned about the pH of their substrate, because it has such a profound effect on the availability of nutrients. So I want to take a closer look at pH and what that actually is, because I find a lot of people, we talk about pH, we measure pH, but we don't know, we don't have a really good feel for what it is. Water, as we know, is H2O, or 2 hydrogen molecules for every oxygen. And so in pure water, about 1 in 10 million molecules will split apart. That's a very small number, but it actually has very profound consequences. And they will split into a hydroxyl ion and a hydrogen ion. Now, when we measure pH, what we're really measuring is the concentration of the hydrogen ions that are in solution. So if you imagine, if you consider these glasses of water, in this first glass, we have an equal concentration of hydrogen and hydroxyl ions. And this pH is said to be neutral, or pH of 7. Now, if we add something to the water, or if we add the water to a substrate and it reacts with that substrate, and some chemical reactions occur that cause more hydrogen ions to be in solution, the pH goes down and it is said to be acidic. And conversely, if we add something to the water, or if the water is added to a soil or a substrate, and it causes a shift where there's more hydroxyl ions and fewer hydrogen ions, the pH increases and is said to be more basic. But what's really important to know is that when we measure pH, we're measuring the pH of this solution, not the particles, not the substrate, but the solution within the pH. When you irrigate a crop and you water that crop, you water the container, and very quickly that water will react with the substrate particles, and it'll affect the pH especially, but it'll also affect to some extent the nutrients that are in solution. So what we'd like to be able to do is measure the pH of this solution, or measure the quantity or the concentration of nutrients in that solution. And many of you may have seen charts like this that show you how nutrients become available in a soil. This is for mineral soils, this is for organic soils, as a function of pH. So if you have a pH of 5, some of these nutrients are not available, but they become relatively more available as you move up into pH 6 or 6.5, etc. Now, if you have this chart for organic soils, this is not necessarily the same as the organic media that we use in our containers. This refers mostly to soils that have a high peat content, or these muck type soils that are in some parts of the country, including Ohio. This is a chart that was made at Ohio State University many years ago, but I've done a lot of work looking at nutrient availability as a function of pH in pine bark substrates. And I believe that this chart showing the relative availability of nutrients as a function of pH is pretty accurate for most soilless substrates. So this one developed specifically for our container media. This is the one you should refer to if you're going to use these charts. But what it shows is that just how influential pH can be on nutrient availability in a container. So one of the things that we'd like to do is measure the pH, the electrical conductivity, or the nutrient level in this soil solution. So this is a series of figures that a student had done for me several years ago, and they're somewhat crude, but they really demonstrate quite nicely what happens. What we like to do, a method that is very popular and used by many nurseries and greenhouses, is this pour-through method. And it is a very good way to extract the solution that's within the container, and so that we can measure it for the pH, the electrical conductivity, or in some cases, the nutrient availability. There are many articles written on how to do this, so you can find a lot of this information on the internet. I see some common problems with this method, so I wanted to illustrate some concept and how to do this more consistently over time, and how to get better results using this method. Now, consistency is critical, so using the same person and the same equipment and the same protocol over time is very important. This is a setup we use in our lab, and this method is so, well, in my experience, it's so accurate. We use this in our research program, so I think it is certainly something that can be used in greenhouse and nursery production. But we get these clear saucers. You can get these from any of the big box stores. We cut little sections of 3-inch PVC pipe, And we set the PVC pipe inside the saucer and put the container on top of it, so that when we do the pour through, the container can drip into the saucer and it's not sitting into that solution that's dripping out, and you get a much cleaner solution, and it's easier to measure that then, and it's not contaminated with some of the substrate particles that come out of the bottom of the pot, etc. So again, what we want to do is we want to get the solution out of this container. Now, this is just an illustration. We don't actually pour red water on the top of it, but we drew this in red just to prove the point. What we'd like to do is add water to the surface of this container that forces the substrate solution into the saucer so that we can measure it. What I see in a lot of nurseries is when they pour this solution onto the surface, we get a lot of channeling, especially down the edges of the pots, so that the solution that we're collecting in the saucer is contaminated with this water. We don't want that. What we want is we want to extract this solution so that we can measure it, because this will give us more accurate information on the chemical properties of this substrate so that we can make fertilizer decisions, etc. So we want to avoid this situation, and if you consider like a piston flow, we want this water to push the water out of the bottom. Now, the way to do that is when you're pouring the water, to pour it slowly around the center or the middle of the container. Avoid the edges. We've done a lot of research in refining this method, and we found that if you do this and you pour the water slowly, you get very accurate results with virtually no contamination of that poured water down into the saucer. So I want to make a few comments about substrate stability. One of the things that, this is especially true for long-term nursery crops, is shrinkage in the container. And what I mean is you fill a pot up, you pot your plant, and several weeks or a month later, you see the level of that media going down in the container. That is a real problem, especially for nurseries and greenhouses that try to use compost and other, agricultural byproducts that they may be able to find locally. Now, one thing that's really important in determining substrate stability is the cellulose, hemicellulose, and lignin content of the media. And most important, the value that you really want to know is the lignin content. Lignin is very resistant to decomposition. So when you look at the lignin content of organic matter, the higher that number, the more stable that material will be over time. Peat moss has a lignin content of about 5 to 10%, while pine bark has almost 40% lignin. And that's one of the reasons why pine bark is used in long-term nursery crops that are grown outdoors, because sometimes these crops are grown for 6 months or 1 or 2 years. And in fact, when you use peat moss, it will start to break down much more quickly than pine bark will. Pine bark also happens to be a lot cheaper too, and that's another reason why it's used more in nursery crops, but it also is more stable over time. So one of the decisions that is often made with respect to substrate management is, should you change your substrate? Should you add new components or remove certain components that you have been using before? And for example, one of the really common questions we're getting now is, there's these new wood fiber substrates that a lot of nurseries and greenhouses are exploring as a replacement for perlite, or just as a replacement for peat moss. So should you use these materials? And of course, one of the things you have to consider is cost. And is the product really less expensive? Do you need to change your infrastructure? Do you need to store these materials differently? And then how it affects the crop itself. When you're looking at changes to the media, there will be some immediate changes. Some of these materials will have an effect on the chemical properties, especially the pH, the physical properties, and the biological properties. Another consideration are the long-term changes in the crop, which we talked about would be mostly degradation and shrinkage of the substrate over time. Now, one of the things that I've found is that the smaller the plant, this is especially true for plugs, they are very sensitive to even subtle changes in the substrate. So you have to be very careful before you change substrates, especially if you have a material that works really well. You don't want to change that just on a whim. You have to be very careful, especially with smaller plants. Now, larger woody plants, because they're larger, they're far more robust. They're not as sensitive to small changes in the substrate. In fact, Ted Bilderback always used to say, you could add up to 20% of anything to a container and it probably won't change anything. That is sort of generally true for large containers and large nursery crops, again, because they are not as sensitive. But I don't think that would be true for smaller plants, especially plugs and plants smaller than 1 gallon containers. Now, something very much related to that, short-term crops, which also tend to be smaller plants, you have to be really concerned about the immediate changes in the chemical and physical properties, root sensitivity, how will this change your irrigation requirements. But longer-term crops, which again tend to be larger plants or outdoor nursery crops, you have to be probably more cognizant of how the substrate will be stable over time. Will there be premature degradation of that material relative to a pine bark or something that is very stable that is typically used? Well, I was going to go through a case study in biochar, but I think we're running out of time. We studied biochar a lot in our research program over the past 5 years, and this just exemplifies this idea that you can't look at the individual components, you got to look at how these materials respond once they're blended together. And what we found is that biochar, while it has some very unique properties alone, when you add it to a commercial mix, especially at a 10 to 20% volume, it really has very little effect on the substrate. Plants grew fine. But, and I don't have the time to go into details here, but the important thing is, if you change your substrate or if you change some sort of management aspect, you have to look at the finished substrate and how those properties have changed instead of just looking at individual components. Science, we have tried. We do not do a very good job at predicting the physical chemical properties of a media just knowing the components. You would think that would be possible, but all the attempts that have been made in the scientific literature so far have done a very poor job at trying to predict what the properties would be of a substrate after it's mixed up. So again, for the 4 functions of the container media, the physical properties would be the first 2, the chemical properties, and this long-term, providing anchorage to the plant, the stability of that substrate over time. Now, so with that, I think I'm running out of time here, but I do have time to answer a few questions.
Rosa, do you want to do the question?
Thanks, Dave. That was great. Yeah. So one of the questions that came right now is, can you explain a little bit more what biochar is?
Okay, yes, sorry. Biochar, there was interest in biochar. If you take an organic matter and you heat it to high temperatures in the absence of oxygen, what will happen is a lot of the compounds within that organic matter will volatilize. They'll turn into a gas. Well, then you can collect that gas and you can turn it into a form of gas or oil that then has other uses for energy and so forth. What you are left with in the bottom of that chamber then is this black charred organic matter, very similar to charcoal, to be frank with you. So now what happens is, so there was a lot of, when there was more interest maybe 10 years ago in this system called pyrolysis, where you generate lots of biochar in an effort to create these gases and biofuels. And what we are left with was this charred organic matter. So that's what biochar is. It's basically charred organic matter, blackened organic matter. And that has certain interesting properties in poor soils. In certain areas near the equator where they have poor soil types, adding biochar to those soils actually improved the chemical properties and the productivity of those soils in growing crops. What we have found is that in growing media, it has fairly little or no effect on the media itself. So they have not gained a lot of traction. And right now, because there's less interest in these biofuels, because gas and, they're extracting gas and oil out of rocks and so forth, the availability of biochar has gone down over time, and so it's rather expensive. It's hard to find. It doesn't really improve much in terms of container quality, but if you want to email me, I can send you a lot more information on biochar and the work that we've done. That's a real long answer to a. Yeah, sorry about that, but that's.
We have a couple more questions. So the other question is if you can talk a little bit about nutrient availability when you compare cocoa-based media, I assume comparing it to peat-based media.
So what is the nutrient availability? Well, there were some initial problems with salt toxicity in the cocoa media. I don't think that's such an issue anymore. I think the quality control of that material has been improved greatly over the last 5 to 10 years. So in terms of nutrient availability, there is nothing that I have read in the literature that really jumps out at me in terms of major differences between sphagnum peat moss and cocoa coir. In fact, the pH of cocoa coir may be just a little bit higher, but not greatly so. And you shouldn't notice drastic changes to your fertility program when you're using those two media components.
And that same person follow up by asking, how do those two compare to rock wool or other organic substrates?
Well, to rock wool is going to be more of a hydroponic type material, whereas coir and peat moss in typical containers, you're going to mix that with other components, and there probably are measurable changes, but not drastic ones. Is the short answer I could give.
Okay. And then another question is whether you know if there's any comparable alternative to peat, one that might be a little bit more sustainable.
Well, sustainable alternatives to peat right now, coconut coir, I think, is an excellent one. And the reason is it has some of the same physical properties, its ability to absorb and retain water, similar to peat moss. Now, it is different, so you have to do your homework and don't change everything at once. But I believe coconut coir has great potential. There is a new wood fiber material that is being pushed. It can't replace all of the peat moss, but they're finding that it can replace up to 40%. Now, one of the problems that I notice is we've been using peat moss for 60 years, and we've been refining and studying and perfecting the use of peat moss in containers for many decades. We have these new materials like coir and wood fiber. They won't be perfect initially, but as we continue to work with them, especially the grower community, I think those materials can replace part or all of peat moss in the future. But it will take a little more work, a little more experience, and a little more research till we get to that point, because peat moss is so well established and it's been so highly studied. It's just very difficult to compete with sphagnum peat moss, right now. It just requires more work and more refinement.